Chapter 7: Smart Contracts and Solidity. As we discussed in the intro chapter, there are two different types of accounts in Ethereum: externally owned accounts, EOAs, and contract accounts. EOAs are controlled by users, often via software such as wallet applications that is external to the Ethereum platform. In contrast, contract accounts are controlled by program code, also commonly referred to as smart contracts, that is executed by the Ethereum virtual machine. In short, EOAs are simple accounts without any associated code or data storage, whereas contract accounts have both associated code and data storage. EOAs are controlled by transactions created and cryptographically signed with a private key in the real world external to and independent of the protocol, whereas contract accounts do not have private keys and so control themselves in the predetermined way prescribed by their smart contract code. Both types of accounts are identified by an Ethereum address. In this chapter, we will discuss contract accounts and the program code that controls them. What is a smart contract? The term smart contract has been used over the years to describe a wide variety of different things. In the 1990s, cryptographer Nick Szabo coined the term and defined it as a set of promises specified in digital form, including protocols within which the parties perform on the other promises. Since then, the concept of smart contracts has evolved, especially after the introduction of decentralized blockchain platforms with the invention of Bitcoin in 2009. In the context of Ethereum, the term is actually a bit of a misnomer, given that Ethereum smart contracts are neither smart nor legal contracts, but the term has stuck. In this book, we use the term smart contracts to refer to immutable computer programs that run deterministically in the context of an Ethereum virtual machine as part of the Ethereum network protocol, in other words, on the decentralized Ethereum world computer. Let's unpack that definition. 1. Computer programs. Smart contracts are simply computer programs. The word contract has no legal meaning in this context. 2. Immutable. Once deployed, the code of a smart contract cannot change. Unlike with traditional software, the only way to modify a smart contract is to deploy a new instance. 3. Deterministic. The output of the execution of a smart contract is the same for everyone who runs it, given the context of the transaction that initiated its execution and the state of the Ethereum blockchain at the moment of execution. 4. EVM context. Smart contracts operate with a very limited execution context. They can access their own state, the context of the transaction that called them, and some information about the most recent blocks. Finally, decentralized world computer. The EVM runs as a local instance on every Ethereum node, but because all instances of the EVM operate on the same initial state and produce the same final state, the system as a whole operates as a single world computer. Life cycle of a smart contract. Smart contracts are typically written in a high-level language, such as Solidity. But in order to run, they must be compiled to the low-level bytecode that runs in the EVM. Once compiled, they are deployed on the Ethereum platform using a special contract creation transaction, which is identified as such by being sent to the special contract creation address, namely 0x0. Each contract is identified by an Ethereum address, which is derived from the contract creation transaction as a function of the originating account and nonce. The Ethereum address of a contract can be used in a transaction as the recipient, sending funds to the contract, or calling one of the contract's functions. Note that, unlike with EOAs, there are no keys associated with an account created for a new smart contract. As the contract creator, you don't get any special privileges at the protocol level, although you can explicitly code them into the smart contract. You certainly don't receive the private key for the contract account, which in fact does not exist. We can say the smart contract accounts own themselves. Importantly, contracts only run if they are called by a transaction. All smart contracts in Ethereum are executed ultimately, because of a transaction initiated from an EOA. A contract can call another contract that can call another contract, and so on, but the first contract in such a chain of execution will always have been called by a transaction from an EOA. Contracts never run on their own or in the background. Contracts effectively lie dormant until a transaction triggers execution, either directly or indirectly as part of a chain of contract calls. It is also worth noting that smart contracts are not executed in parallel in any sense. The Ethereum world computer can be considered to be a single-threaded machine. Transactions are atomic, regardless of how many contracts they call, or what those contracts do when called. Transactions execute in their entirety, with any changes in the global state recorded only if all execution terminates successfully. Successful termination means that the program executed without an error and reached the end of execution. If execution fails due to an error, all of its effects, changes in state, are rolled back as if the transaction never ran. A failed transaction is still recorded as having been attempted, and the ether spent on gas for the execution is deducted from the originating account, but it otherwise has no other effects on contract or account state. As mentioned previously, it is important to remember that a contract's code cannot be changed. However, a contract can be deleted, removing the code and its internal state from its address, leaving a blank account. Any transactions sent to the account address after the contract has been deleted do not result in any code execution, because there is no longer any code there to execute. To delete a contract, you execute an EVM opcode called self-destruct. That operation costs negative gas, a gas refund, thereby incentivizing the release of network client resources from the deletion of stored state. Deleting a contract in this way does not remove the transaction history of the contract, since the blockchain itself is immutable. It is also important to note that the self-destruct capability will only be available if the contract author programmed the smart contract to have that functionality. If the contract's code does not have a self-destruct opcode, or it is inaccessible, the smart contract cannot be deleted. Introduction to Ethereum high-level languages. The EVM is a virtual machine that runs a special form of code called EVM bytecode, analogous to your computer's CPU, which runs machine code such as x86-64. We will examine the operation and language of the EVM in much more detail in the EVM chapter. In this section, we will look at how smart contracts are written to run on the EVM. While it is possible to program smart contracts directly in bytecode, EVM bytecode is rather unwieldy and very difficult for programmers to read and understand. Instead, most Ethereum developers use a high-level language to write programs and a compiler to convert them into bytecode. While any high-level language could be adapted to write smart contracts, adapting an arbitrary language to be compatible to EVM bytecode is quite a cumbersome exercise and will in general lead to some amount of confusion. Smart contracts operate in a highly constrained and minimalistic execution environment. In addition, a special set of EVM-specific system variables and functions needs to be available. As such, it is easier to build a smart contract language from scratch than it is to make a general-purpose language suitable for writing smart contracts. As a result, a number of special-purpose languages have emerged for programming smart contracts. Ethereum has several such languages, together with the compilers needed to produce EVM executable bytecode. In general, programming languages can be classified into two broad programming paradigms: declarative and imperative, also known as functional and procedural, respectively. In declarative programming, we write functions that express the logic of a program, but not its flow. Declarative programming is used to create programs where there are no side effects, meaning that there are no changes to state outside of a function. Declarative programming languages include Haskell and SQL. Imperative programming, by contrast, is where a programmer writes a set of procedures that combine the logic and flow of a program. Imperative programming languages include C++ and Java. Some languages are hybrid, meaning that they encourage declarative programming but can also be used to express an imperative programming paradigm. Such hybrids include Lisp, JavaScript, and Python. In general, any imperative language can be used to write in a declarative paradigm, but it often results in inelegant code. By comparison, pure declarative languages cannot be used to write in an imperative paradigm. In purely declarative languages, there are no variables. While imperative programming is more commonly used by programmers, it can be very difficult to write programs that execute exactly as expected. The ability of any part of the program to change the state of any other makes it difficult to reason about a program's execution and introduces many opportunities for bugs. Declarative programming, by comparison, makes it easier to understand how a program will behave. Since it has no side effects, any part of a program can be understood in isolation. In smart contracts, bugs literally cost money. As a result, it is critically important to write smart contracts without unintended effects. To do that, you must be able to clearly reason about the expected behavior of the program. Therefore, declarative languages play a much bigger role in smart contracts than they do in general-purpose software. Nevertheless, as you will see, the most widely used language for smart contracts, Solidity, is imperative. Programmers, like most humans, resist change. Currently supported high-level programming languages for smart contracts ordered by approximate age include 1. LLL, a functional programming language with Lisp-like syntax. It was the first high-level language for Ethereum smart contracts, but is rarely used today. 2. Serpent, a procedural programming language with a syntax similar to Python. Can also be used to write functional code, though it is not entirely free of side effects. 3. Solidity, a procedural programming language with a syntax similar to JavaScript, C++, or Java, the most popular and frequently used language for Ethereum smart contracts. 4. Viper, a more recently developed language, similar to Serpent and again with Python-like syntax, intended to get closer to a pure functional Python-like language than Serpent, but not to replace Serpent. Lastly, Bamboo, a newly developed language influenced by Erlang, with explicit state transitions and without iterative flows, such as loops, intended to reduce side effects and increase auditability, very new and yet to be widely adopted. As you can see, there are many languages to choose from. However, of all of these, Solidity is by far the most popular, to the point of being the de facto high-level language of Ethereum, and even other EVM-like blockchains. We will spend most of our time using Solidity, but we'll also explore some of the examples in other high-level languages to gain an understanding of their different philosophies.